Hi everyone, so in this video we resume our discussion on the statistical assumptions that are imposed by different recurrent neural network architectures. And here we focus on the conditional independence assumptions. So basically assumptions on the conditional probability distribution of the target labels given the input, right? And this is basically what the network is trying to estimate, or what the network is trying to use in training, use the raw training labels and the raw input vectors to model a function of the output given the input, right? So so far we discussed the networks with hidden to hidden recurrence only and networks with output to hidden recurrence only. So networks that only have a connection from the hidden unit in one time step to the hidden unit in the next time step, and networks that that only have a connection from the output unit in one time step to the hidden unit in the second time step. So let's focus on these two types of networks and see what kind of assumptions we have in terms of conditional independence. So let's take the hidden to hidden recurrence, right? So the recurrence, or the connection between one time step to another, is only a connection between the hidden state in the current time step to the hidden state in the subsequent time step. So here, if we think of the probability of y of 1, let's say I have a sequence of tau points, of tau elements, tau time steps, then the probability of y of 1, the joint probability of y of 1 up to y of tau, given x of 1 up to x of tau, is basically equal to a product of all the time steps, the probability of y at that current time step, given the current and previous inputs, which is x of 1 up to only x of t, right? So if t equal 2, then this is probability of y of 2 given x of 1 and x of 2, right? Why does this model impose this assumption? It's very simple, because in order to estimate y of 3, right, in order to estimate the third output, right, in order to which mimics y of 3, right? So remember, y is the training target, right? O is the output of the neural network. In order to estimate O of 3, you need to know x of 1, x of 2, x of 3. That's all you need to know. You don't need to know anything about the training label y of 2 or the training label y of 1, right? And if you know these values of the x's, right? Because x of 1, x of 2, x of 3 will make you able to compute h of 3, right? So from x of 1, h of 1. And then from h of 1 and x of 2, right? So you have x of 1, you compute from it h of 1. And then from h of 1 and x of 2, you compute h of 2. And then from h of 2 and x of 3, you compute h of 3. And then you compute O of 3, right? And O of 3 is what you use to basically estimate. So this is the loss y of 3. Right? So in order to estimate y of 3 given x of 1 and x of 2 and x of 3, you don't need to know any future x value. You don't need to know any past or future y value. Right? So this is a conditional independence, right? So whenever we have a joint probability that decomposes into a multiplication of individual probability distributions, so we say that we have a conditional independence of the target labels, of the outputs, the y of t's, given the inputs. Not only that, every y of t depends only on the current and previous values. It doesn't depend on the future values, and this is called a causality assumptions, right? So they impose a causal structure, because the output at a given time step depend only on past and current inputs. It doesn't depend on future inputs. So there is a causal structure imposed by this network, and that's one. Another is that there is an assumption of conditional independence of the outputs given the inputs, right? And of course, as we mentioned last time, we also have a stationarity assumption of the state transition, meaning the state-to-state transition is a stationary process because this W right here does not depend on time, does not change from time 1 to time 2, right? So the assumptions imposed when you use a network like this: stationarity of the state-to-state transition process, causality, conditional independence of the output given the input, right? How about this network? If I add to this network a connection of output to hidden, and I use teacher forcing in training so that the output to hidden is replaced by a target label to hidden. So y of 1 is connected to h of 2, y of 2 is connected to h of 3, y of 3 is connected to h of 4, right? Then I completely removed the conditional independence assumption, right? The causality assumption is still there, but the conditional independence assumption is removed by this connection, meaning that in order to estimate y of 3, in this case, if I add this connection, then I would need to know the values of y of 2, even given x1, x2, and x3. I still need to know the values of y of 2 and y of 1. Why? Because y of 1 will affect h of 2, and y of 2 will affect h of 3. Right? So in these two cases, in this case, I don't have conditional independence anymore. I still have causality, right? Now let's say I have a network like this, where the whole input sequence is connected to all the hidden units of all the time steps. So if the input sequence length is 100, then the whole 100 element vector of the input, this feeds into the hidden units of all the time steps. Then I no longer have causality, right? So this network, which we called it network type A and type B, they have causality. A has conditional independence of the output given the input. This network here, let's call it C, has conditional independence of the output given the input. This network does not have conditional independence of the output given the input. Sounds good? So, and of course, when you reflect an assumption, if you are correct, if that assumption is followed even approximately for the data generating process, then that will improve your generalization performance. If it's not followed, then it will cause underfitting, right? So you will not be able to fit even the training data. Now, the causality assumption that is followed in these two, right? That will be the topic of the next video. We will discuss recurrent neural networks that actually violate causality, right? And when is that useful? So here, there is no causality with respect to the inputs, right? But we will discuss more general networks that violate the causality assumption, right? Here, there is no causality with respect to the inputs because future inputs affect the current hidden state. Now, one last assumption. In A and B, we assume that the input X and the output O, as well as the training labels Y, have the same sequence length, right? So if the input has sequence length of 100, the output will have sequence length of 100, right? In that network here, not necessarily. The input can have a different sequence length than the output, right? That will also be the topic of the videos after next, for 2 videos after the coming one. What if you don't have equal sequence lengths, and how to determine the output sequence length? Okay, sounds good. Thank you.